All right, so here we go. Section 18.3. The last section in the last chapter for the semester. So when we're done with this one, that's it. All right, section 18.3 is entitled Special Probability Density Functions. And in this section, we're going to take a look at two special probability density functions, the uniform distribution and the exponential. So what we're going to do is we're going to cover two types of distributions that are common enough to have their own classification. I mean, they happen often enough that they get a fancy name, but more importantly than a fancy name, because they're common enough, the approach to solving questions about them has been really standardized. There's formulas to do things, and it takes away some of the difficulties that we would have had in section 18.2 with finding means or standard deviations. All right, so the first one we're going to take a look at is called the uniform distribution. And a uniform distribution is a probability distribution that occurs when the probability for the random variable remains constant across the entire interval. That is, that for any value x in the interval a to b, the probability is always the same, right? It looks like this right over here, this picture that we're looking at. And so for some interval a to b, I don't know what those numbers are, but the problem will tell me, the probability for any value between a and b is always the same. So we get this effectively a little rectangle where the height is always just 1 divided by b minus a. Now, if you're wondering why that's true, it goes back to the definition of a probability model. Remember the definition that said that area had to be equal to 1? And since it's uniform, that makes it a rectangle. And the formula for the area of a rectangle is length times width. And the length being the bottom down here, the length is going to be b minus a. And I got to multiply that by the, wait. Let me change my definition so it fits this picture a little better. Let's go with this definition. Base times height. How's that sound? And then the base is going to be this bottom down here. It has a length of b minus a, and I've got to multiply that by some height h that makes it always be equal to 1. And so the way that you get an answer of 1 when you multiply is you multiply something by its reciprocal. And so then no matter what number this ends up being, this just is the reciprocal. So if my base ended up being a 5, that would just be 1/5. Or if my base ended up being a 12, then that would just be 1/12. Or if my base ended up being a 7th, it'd be 1/7. Okay? Now, these ones are pretty obvious. They're pretty easy to see. But what if the base ended up being something ugly? What if the length of that base down there ended up being like 5/3? Well, I know I have to take the reciprocal, so then the reciprocal would have to be 3/5. So if this distance from here to here worked out to be 5/3, then this height would have to be 3/5. Now the shortcut to this is always just use the formula. And the formula just simply says that if you know its uniform distribution, so if we know that it's uniform, then the probability distribution function, or the probability density function, those two phrases are used interchangeably. It really depends on who wrote the book, is always just 1 over b minus a. And then if you can, and it's not always going to be true, but if you can, simplify that. Now, the nice thing about this is it makes calculating the mean and the standard deviation almost trivial. The mean is always this, and then the standard deviation is always that. The mean is always 1/2 times the sum of a and b, and the standard deviation is always 1 divided by the square root of 12 times the quantity b minus a. Now, again, depending on who wrote the book, you will sometimes see this one written differently, because sometimes they will do this. And they will simplify that denominator, and then some people will go even further and write this as root 3 over 6 times b minus a, which is just the 1 over 2 root 3 rationalized. So multiply the numerator and denominator by root 3, and you get a root 3 upstairs, and then the root 3 gives you a 3 downstairs, but times 2 is 6. So while this textbook uses this version, some textbooks use that version, some textbooks use that version, but what always stays the same as soon as is always b minus a. All right, let's take a look at an example. All right. The amount of insurance sold by a particular agent is uniformly distributed over the interval 10 to 85 measured in thousands. So the amount of insurance that they sell in a day is somewhere between $10,000 and $85,000 worth of insurance, and it's uniformly distributed. Okay? So that fact that it's uniformly distributed tells me that that's going to be my A, that's going to be my B, and that my probability density function is going to be 1 divided by B minus A, or 1/75th. Okay? All right. There's my probability density function. What amount of insurance does he sell in an average day? Well, that's asking for the mean of this probability model, or if you prefer, the expected value of this probability model. And I got a formula for that. The formula says that's always 1/2 times A plus B, or for this specific example, it's going to be 1/2 times 10 plus 85. 10 plus 85 is 95. So 95 over 2, and 95 over 2 is what? 2.5 shy of 50. So 47.5. So $47,500 per day. So the expected value, or the average, is $47,500 per day. Well, that's not too bad. All right. What's the next question? What is the probability, or find the probability that they sell more than 50,000 on a given day? Well, because we're doing continuous probability models, I know that the probability that my random variable is more than some value A just means to do an integral from the A value to the upper limit. And so for us, since they want it to be more than 50, we're going to do an integral from 50 to 85. Now I got the 50 from here, but where'd the 85 come from? Well, the 85 came from here, that this function is only valid, this probability density function is only valid up to 85. And then my integrand is just 1/75 dx. And so that's going to be 1/75 x evaluated from 50 to 85. So that gives me 1 over 75 times 85 minus 50, 30, oops. And that gives me what? That my mean, or my probability that my random variable is greater than 50 would be 85 minus 50 is 35. So 35/75. I think that reduces. Let's grab the calculator and see. So 35/75. Oops. 35/75 is about 46%, 47%, round where they would tell me to round it. So there's about a 47% chance, just about a half, about 50%, close, 47% chance that this particular agent, that's how they've defined it up here, will sell more than $50,000 on a given day. So uniform distribution. It's a special type of distribution. It just shows up here and there. But it's nice because it's super easy to come up with a formula, and it's super easy to come up with a mean and a standard deviation. All right, sorry about that. Someone knocked on the door, came to my office hours. It was nice. Let's see. So we found our probability for a uniform distribution, and we calculated some means for it because we got these nice formulas. Let's try another one. The lifespan of an insect is uniformly distributed over the interval 20 to 36 measured in days. So some bug out there lives between 20 and 36 days, and the probability that their life will be X number of days between 20 and 36 is uniformly distributed. So this bits and pieces, uniformly distributed, 20 to 36, that sets everything up. That tells me that the probability density function is going to be 1 over b minus a, where a is equal to 20 and b is equal to 36. So when I put that all together, I get that for this bug, my probability density function is 1 over 16. That's going to be the 30 minus the 26. Okay? Now it also wants to know, what is the expected life for this bug? Well, the mean is always 1/2 times a plus b. And so when I figure it out for this guy right here, I'm going to get that the mean is 1/2 of 20 plus 36. So that's going to be 10 plus 18. So that's what, 28? And of course, these are going to be days. What does that tell me, though? Well, that tells me that the mean is 28 days, or that the average lifespan for this bug is 28 days. All right. Find the probability that the insect lives within 1 standard deviation of the mean days long. Uh-oh. In order to do that probability, though, I need to know a standard deviation. So let's go ahead and get that standard deviation. Standard deviation is 1 over the square root of 12 times b minus a. And so when I figure that out for this specific example, that means that my standard deviation is 1 over the square root of 12 times b minus a, and b minus a here is 16. So that's going to give me 16 over 2 root 3. So that's 8 over root 3, and I don't know what that number is, so I'm going to approximate it with my calculator. 8 divided by the square root of 3, and I get approximately 4.62, so I'll call that 4.62. All right, now that I have a standard deviation, I can figure this out. Now, this is similar to the problem we did below, that within 1 standard deviation of the mean means 1 below to 1 above. So I'm going to do an integral from the mean minus the standard deviation to the mean plus the standard deviation of my probability density function. And then when I plug in the values and make that be for this example right here, that's going to be, let's see, down here, this is going to be 28 minus 4.62. This is going to be 28 plus 4.62. My probability density function is 1/16 dx. And so I'm going to go ahead and figure that out. These are actually really easy to do by hand because this is so easy to integrate. So that's going to give me 1/16 x from 28 plus 4.62 to 28 minus 4.62. Geez, I'm going to clean that up because that looked horrible on both of them. Now you might be wondering, why is he being so lazy and not figuring this out? That'll become apparent here in a moment, right? When I calculate this, so I'm going to get that the probability that we're within 1 standard deviation of the mean is going to be 1/16 times that minus that. 28 plus 4.62 minus 28 plus 4.62. Now, if you're thinking I made a mistake there, I distributed the negative into both terms. So the 28 that was positive became negative, and the 4.62 that was negative became positive. And now I'm hoping that you're seeing why I was being lazy. And I just get that, whoa, go away. I just get that that works out to be 1/16 times 2 times 4.62, or I'll toss that in the calculator. And that's going to be, let's see, what's that going to be? That's going to be 4.62 divided by 8, which is about 58%. So approximately 58%, round wherever they would tell me to round it to. Okay. Now, here's a good question. This is a question that I don't have an answer for. Since I had to throw this final step into the calculator, why didn't I throw just the original problem in the calculator? And I could have done that. I could have gone back and just done this whole problem in the calculator and said, set up my integral. My lower limit is 28 minus 4.62. My upper limit is 28 plus 4.62. My integrand is 1/16, and respect to x, and I get 0.5775. Same answer. I don't know. It's up to you. I'm not going to make anyone do this stuff by hand. I'm just showing them that it can be done by hand. All right. We're at 15 minutes, so I'm going to stop right there. When I come back, I'll do the second part of this video, which will deal with the other special probability model, that is the exponential distribution. All right, see you back here for part 2.